welcome back, Zoomers, Roomers. Happy Thursday. Happy garbage day to those of you who celebrate on Thursdays as opposed to Tuesdays, of course.
Thank you.
Yeah. And I got the screen share going, so you should be able to see that. So what are we talking about in this unit? We start with the beach. That's a much nicer thing to look at. We started a new topic on Tuesday. What is it? Roomers, Zoomers. I'm watching the chat, or you can talk to me. Either way. Invariance, yeah. Give me another synonym for invariance. Weak or strong factorial invariance. Yep, those are flavors of invariance or levels of invariance, you could say. Factorial invariance is the term that gets used in CFA a lot. If you're talking to a more of a layperson audience, scalar is another type of invariance. I would say equivalence is an easier word for most people to understand than invariance. And if you're talking to an IRT crowd, what are you talking about instead? Ding, differential item functioning, and that is an antonym, not a synonym, because it's from the opposite perspective. It refers to non-invariance, which is a mouthful, or not the same is the way you'll hear me say it. Same or not the same? So yeah, so we got answers about the levels of invariance. So what's the first one? What's the first level that you have to pass in order to keep going? It starts with a C. Give you a hint. It's whether your factor configuration is equal across groups. Configure roll for the win, yeah. So that is the idea of factors having basically the same intent across groups. So let me get to, step one. So do you have the same general factor structure? Do you have the same items loading on the same factors and the same number of factors? And this, if you don't pass this stage, there's no point in going further because all of the questions would be moot because the factors don't mean the same thing. So this one is a prerequisite that we would want to have no matter what. And I showed a couple examples of when this would not hold. So for instance, on slide 9 here, we have items measuring different factors across the groups. So even though you could describe this as a 2-factor model where you have 3 indicators each, it's not the same 2 factors because they have different indicators. So it wouldn't make a lot of sense, for instance, to ask if the loading for item 5 that goes from factor 1 to item 5 is the same loading for item 5 that goes from factor 2. It's not the same idea. So if you have this, there's no point in keeping going, but most of the time people can have something to work with. So here's an example of when you might have a different factor structure, but you can make it work. The bottom, group B, has a factor, really a single factor model is what it needs, and the top group wants 2. That can be operationalized by constraining the correlation between the factors to 1, and then that is essentially a 1-factor model instead. So then you can go through the same types of steps, and eventually you may be able to test whether or not the factor covariance is different. Factor correlations are different. So that's a step we haven't talked about. If you pass this step, what's next? Metric. Synonyms for metric, what are they? Weak, yep. And what is metric focused on? What kind of parameter? The loadings, yeah. See, that's the nice part about there being fewer people is that you get more opportunities to participate if you so choose. Yeah, loadings. That is, I think, to most people the most important part because that's really about what the factor means. And if you don't have metric invariance, then that means the way that the items are being predicted by the factor is different. The slopes are different. Some items might be more important in some populations than others. And so then it becomes questionable whether you're really talking about the same thing. And if we want to test the loadings, what do we need to do at that stage? Also, we have to free something in order to constrain the loadings equal. Do you remember that?
Factor variance.
Yeah, factor variance. So if we look at, for instance, the M plus example we started last time, the configural model in this example is using binary gender as the groups. Women are going to be the reference and men are the alternative. And in the code, the model part So the blue colon as recognized as a keyword for M+, that left side here for the reference group is going to stay the same through all the stages. We don't change this side. What we are changing is how the model for the alternative group, men in this case, differs from the configural model for the reference group. So at this stage, everything differs because this is configural, and that's because we're not using, let's go over here, the same labels. So the fact that these labels are on the loadings for the reference group, but not here for the alternative group, means they get to be different. Same thing with the intercepts, same thing with the residual variances, error variances as I'm trying to call them. Same thing with the error covariances, and then each group needs to have their factor identified separately. So I'm identifying the factor within each group by fixing its mean to 0 and its variance to 1. And do you remember what I said last time? Are the groups on the same scale at all at this stage? Are they comparable in terms of their factor? No, they are not. So just because they both have a factor mean of 0 does not mean that 0 means the same thing. It's like if the factor mean for women were 6 and the factor mean for men should have been 8 and I set them both to 0, then we can't tell that there should have been differences. So we won't be able to actually compare anything with respect to the factors or the measurement model until we get linkage across the two by constraining things to be equal. So at this stage, what we're looking for is good enough fit, because everything else that we'll do to the model in terms of putting constraints is going to harm the fit in terms of likelihood. It may improve the fit in terms of the alternative measures because they're assessed not necessarily the same way. Some of them are relative to a null model, and RMSEA, for instance, is per degree of freedom, so it may get happier as we add constraints. So this one was okay. Then the metric model. So what we did then is add the label for the loadings to the alternative group and simultaneously free the factor variance. So we have to do both of those things at once, otherwise we've imposed a structural constraint as well as a measurement constraint. So at this stage, the groups are halfway equated, essentially. They are sharing a common identification with respect to the factor variance because we're fixing it to 1 in the reference group, but by constraining all of the loadings to be equal, they are linked together. So they're sharing a common factor identification with respect to the variance. They are not yet sharing a common factor identification with respect to the mean. So this is like a half and half kind of deal. And in this example, everything worked perfectly because it's fake. I don't know why people do this in textbooks. It's like they come up with these perfect, well-behaved data where everything works exactly the way it's supposed to be, and then you're supposed to figure out what to do when that doesn't happen. Doesn't really seem fair, but that's the reality. So I started with the perfect example, and then we'll just see all the other ones where things fall apart. So in each case, we are doing a likelihood ratio test against the prior model to ask the question, did the constraints that we imposed, did the simplification that we imposed, did it make the model fit worse? So a non-significant result means not worse, meaning the constraints hold, the loadings are okay being the same across groups, and that would give us an indication that the factor is essentially meaning the same thing. The way the items relate to the factors is the same across groups with respect to their slopes. Okay, is this sounding familiar? Maybe? A little bit. Should be familiar to Vladimir. You had this class before. Yeah. But to be fair, it's not like I can expect anyone to learn this on the first try. Like I remember taking an SEM class and then sitting down to actually do one and being like, I have no idea what I'm doing. And it took a lot of like, oh, what is this about? What is this about? Once you get it into the context of data that you care about, then things, I think, sink in very differently, which is what I'm hoping you will do on homeworks 3 and 5, right? Data that you care about, social capital, yay. Ability, teacher goodness. Can I go with that?
Yeah.
Yeah, what's your trait called?
It really means like epistemic orientation.
Oh, yeah, that's the word I will never, ever remember what it means.
Yeah. Oh, goodness. Really good.
Epistemic orientation. That it's just never going to get into my brain. But You're like the sixth person that I've talked to about that construct across my classes, and I will still never get it. But we'll go with teacher goodness. Yeah, lots of different traits out there. Okay, I think we made it a little bit further than this. So the factor loadings and the unstandardized metric are all being held equal. So the way that the items relate to the trait is the same across groups. And now we can look at group differences with respect to the factor variance. So it's 1 in the reference group, which is women in this case. And in the alternative group, the factor variance was estimated at 0.86. So what that tells us is that the alternative group, which is men in this case, have less variability in depression, at least numerically. 0.86 is smaller than 1. We don't know yet if it's significantly smaller. We'll do that later. That's still coming up, but it is smaller. And the numbers themselves don't really mean anything because this is an arbitrary choice for how we identify the model, but the fact that it's smaller is what matters. Like if I had set this factor variance to 5, then this number would be like, 4 something or whatever. Okay. Then we did the next stage, which is vocabulary words. What comes next? Give me an S. Hey. Give me another S. Strong. Yeah, scalar or strong. And this concerns the item means or the item intercepts. Which is it? Intercepts, yes. And why am I so like, you need to know the difference? What is the difference?
Because they're not necessarily the same, like, in this world.
They're not the same. They can be, but they don't necessarily need to be. So the deal is with the intercepts versus the means. Means are unconditional. Like if you start with an empty model predicting each of these item responses where there's no factor, no predictors, nothing, then the intercept that you would get back is going to be the mean of that item. Like beta 0 as a fixed intercept would be the mean as your jumping off point for a model. The same is true in these models because they're functionally like regression models. Once you add in a predictor, though, the intercept is no longer just the mean of the item, it's the conditional mean, specifically when all of your predictors are 0. So in this context, the predictor is the factor. So the intercept represents the expected item response conditional on a trait of 0. That should hold no matter which group you're in. Because after you control for a person standing on the trait, there should be no difference in their expected response based on group membership. If there is, there's something else the item is relating to that's not the trait that you need to investigate. So the logic of scalar invariance is answering the question, if one group has higher item means across the board, to what extent is that because the group has more of the factor, has a higher factor mean? Because a higher factor mean would trickle down into higher item means across the board. And so to the extent that it's proportionate, then we can say we can hold the intercepts invariant across groups, make them the same, and just let the factor mean be free, and that would be good enough. So we're looking for things that would be disproportionate. Like if a group was lower on one item instead of higher, right? The factor mean being higher couldn't explain that. Disproportionate or unproportionate? I feel like dis is sometimes the wrong word. Disproportionate is the common exception, but yeah. This is what happens when you're a parent, because your children start making up words and it's like, is that right? Unproportionate sounds just fine to me. So, also other funny things that my nieces and my son have said, they once had to leave the house when it was super dark out in the morning, and my niece said, "Why is it moony? Where's this? Why isn't it sunny? It's moony." I'm like, that's not a word, but it very well should be. Like, that makes complete sense to me. Another favorite that I have is when my son learned Christmas songs for the first time. His version of it is, "I wish it were Merry Christmas," which arguably makes more sense, especially if you're 3 and you're waiting for your loot. So, I wish it were Merry Christmas. Not today, pal. It's April. I wish it were finals week. I wish it was finals week. How's that? Yeah, there we go. We can get into it. Anywho, scalar invariance, that's what we're talking about no matter what we wish for. So can we constrain the intercepts and have and release the factor mean and have that be okay? So in this model, I'm on page 6. Intercepts have had their label added to the the alternative group, the non-reference group, and that is putting a constraint on the intercepts. Simultaneously then, we free the factor mean in the alternative group, and it stays fixed for identification to 0 in the other group. So at this stage, the factor is on the same scale across your groups. Now you can talk about which group has a higher factor mean, which group has a larger factor variance, and anything related to that. So now both sides are linked together, and the question is, how much worse did we make the model fit by doing this? And this is interestingly where me and your textbook diverge. So in the textbook, this is from, I forget what chapter it is, but it's in all the chapters are inside the download folder on Icon. In the chapter, the author decided, oh, we have full scalar invariance because the overall omnibus likelihood ratio test was non-significant. Okay, that's a reasonable thing, but I'm concerned about the fact that we're testing 8 things at once. And it could be the case that like 7 of them are fine, but 1 of them isn't, and you wouldn't know that by testing everything at once. So even in the case where you could technically say, yeah, this is good enough, I still tend to look at the modification indices. Now those to review, because I've had a couple questions about those in general, modification indices are otherwise known as score tests in the world of statistics. And my monitor just went blank. Okay, there we go. At least my computer hasn't tried to restart itself yet. And modification indices tell you completely atheoretically and completely in a sample-dependent way how much your chi-square would improve by adding parameters to your model. And what is not shown here is the long, long list of other things it wanted me to add, right? It's still going to suggest error covariances in models with multiple factors. It's still going to suggest cross-loadings and all that other stuff. So I'm limiting my choices to this. Let me think. I think this went over. Hang on. There we go. Column names got booted over for some reason. I'm limiting my choices to just the terms that I enforced invariance constraints on. So that's why I'm only looking at means, intercepts, and thresholds as the label is, because that's the stage I'm at, where it's scalar invariance focused on intercepts. And this is telling me that for item 7's intercept, because it's in brackets and because it says this above it, that the chi-square would improve by 5.89 whatever if I let that intercept differ between women and men. So that is over the threshold for what would improve the model significantly for 1 degree of freedom. And the EPC column here, that's expected parameter change. That is telling you how much the intercept would change by if you release the constraint. So, in English, the intercept for item 7 wants to be higher by 0.16 in women. That's what this is telling you. In parallel, it wants to be lower by 0.2 in men. So I did the math to figure out what the new implied intercepts would be. And this item, by the way, is feelings of worthlessness or guilt. So in this result, it says that after controlling for the latent trait, which is depression in this example, people who have a trait score of 0, even like conditioning on those people, women have a higher predicted response than men by about 0.4. So conditional on a depression score of 0, women are more likely to give higher ratings of worthlessness and guilt. All right. Did I do this one? Yeah, okay. So then in the solution, we now have a factor mean for men, and it works the same way in terms of relative importance being what you care about. So the factor mean for the reference group is 0, and so the factor mean being less than 0 means that in the alternative group, they have a lower factor mean by about 1/10 of a standard deviation. So this has meaning relative to whatever mean you fix the factor to in the reference group only. Question?
Yeah, so
Cheers.
does that mean that for item 7, like there's something besides the factor that is like causing women to have, like, to still answer that even though like their trait is 0.
Yes, so that's exactly right. Let me try to repeat it for the audio. Hang on. Oh, I didn't have the closed captioning on? I thought I turned that on. Sorry about that, folks. So what this means is that there's something else that theoretically is causing women to provide higher responses besides depression. Now, what that is, we can all speculate. That's not my job. I'm not a social psychologist today. I'm not a gender studies person. I try to stick to the things that I've actually have experience with when I pretend to be somebody else. And social is not on that list, but there's likely many, many things that gender is related to that would cause differences in the response to this item beyond depression. So that would be for future research to figure out, or to just say that it's okay. In some cases, it just might make sense that that is the way it is, and it's fine. We still have 8 items that we can hold together with. So when you decide to let some of the constraints go, but not all of them, based on the modification indices and other indices of misfit, that's called partial invariance. And that is another, like, everyone agrees on that term. Everyone agrees that partial is partial, but not everyone agrees on how partial it is. So I would say, as a guiding principle, you want most of your parameters to be invariant. Most. The more that aren't, the harder it gets to defend this idea that it is the same factor across groups. We'll see that in the next example, actually. So partial invariance then is accomplished by giving the alternative group a different label for the same parameter that you want to be free. So in this case, it was the intercept for item 7. So I added a lowercase m, going with the name of the group for men, to separate that from I7 as it is labeled over here implicitly for the women. So you would want to systematically name these things so that you can easily use tools like find and replace, which is case sensitive in M+ and in other programs, so that if you need to alter your code quickly, you can do so. So I'm big on that with the uppercase versus the lowercase because it saves me a lot of time. So at this stage then, there's 2 different types of significance tests that would be relevant to compute. One tells us, are we headed in the right direction? Does the model actually improve after we release the constraint of invariance on item 7's intercept? And that answer is yes. So comparing the previous model where all the intercepts were constrained to this one where we let one go, the difference in the chi-square is about 6, which is significant at alpha of 0.01. So yeah, we're headed in the right direction. Are we there yet, I think is how I would phrase the other one. Like, is this good enough yet? And that involves comparing the last metric model to the current partial scalar model. And in that case, now a degrees of freedom of 7, because we let one of the intercepts go, tells us yes. Non-significant means not worse, means we're done. Hooray. The relevant new output, by the way, is here's what the intercept was estimated to be for women. Here's what it was estimated to be for men, so pretty close to what was predicted. And note that the factor mean has changed as well. So previously, the factor mean in the alternative group was minus 0.11. Now it has changed a little bit to be minus 0.09. So this factor mean difference, that's how you would interpret the factor mean in the alternative group because it's relative to 0, it's the difference. That factor mean difference does not take into account item 7. Item 7 is not part of what makes the factor mean different anymore. So it needs to change if you release one of the intercepts like this. So we can say that there appears to be slightly less depression in men, less so after factoring out these differences in intercepts for item 7. Okay, how are we doing? Everyone's writing. Thumbs? Zoomers? Questions? Any of that you want me to say again? No, not right now. So since item 7 is essentially out of the tournament, we're not going to test its residual variance. You could, but traditionally you leave that part out. If it fails, it's done with the thing. I sometimes break that rule if I don't have very many items and I'm trying to hang on to as much invariance as I possibly can. So to set up that next step, we have the error variance invariance model. That's a mouthful, and there's not a better way to say it other than one other term that you would say. What is the synonym for error variance in terms of levels of invariance? We had weak, we had strong, there's one more.
Super strong.
Super strong. Close. If you have a teacher who won't let you get away with any crap, you would say that they are, that's it, strict. So this model, not letting you get away with anything. Strict invariance. It wants the amount of variance that's due to not the factor to be the same across groups, except for item 7. So note the constraints that I put in here. Leave out item 7 by giving it a different label. So it will have a different error variance estimated across groups as a consequence of that. Yeah, strict. And in terms of structural things, do I need to do anything with respect to my factors at this stage? Nope, head shakes. Nope, I don't. Because this is all about the variance that's not the factor. So there's nothing like compensatory that I have to do at the factor level for this. And this is really how I know these data are fake, because this never holds on the first try, like ever. It's completely unreasonable to expect that the amount of not the factor would be the same, but yet it magically is. So, yay, everything's great. Now this could be the end of the story if you wanted it to be. Actually, nope, there's one more model in this case. I forgot about that. Almost the end of the story. So we still have a difference in intercept across item 7. We maintained a difference in residual variance across item 7, and it looks like the alternative group is more heterogeneous in whatever is not the factor that's related to item 7. The last stage doesn't have a name. It's just error covariances as part of the measurement model. And this one I think you could consider optional, like if a group had an error covariance in one group and not the other, then you just let it be. But in this case, they went ahead and put it in both. So I tested it, and actually that is a typo. That needs to be first. Otherwise it'll be like, why are you trying to star your labels? That doesn't make sense. I'll fix that after class. And in this case, how many degrees of freedom did we save by making the error covariance the same across groups? How many degrees of freedom did we save by constraining the single error covariance equal across groups? No. Don't think too hard. I had 2. Now I have 1. I saved 1. Yeah, so this one is an easier one. And in this case, that 1 degree of freedom was enough to make it worse. P less than 0.04, so I don't need to go to modification indices because I know the one problem that I created. There's no ambiguity here. So whatever relation items 1 and 2 have in their residuals needs to differ across groups. So item 1 and 2 have something else in common that's not depression, and the extent of that commonness is different across groups. So be it. Okay, that could be the end of the story. That finishes the measurement invariance portion of the lines of testing. And so at this stage, the groups are on the same scale with respect to the latent factor of depression. You could do comparisons if you wanted to. You could do add in predictors within each group and look at whether those relations differ across groups. You could do any of that stuff. If you wanted to, if it was of interest, the next stage is called structural invariance, and this pertains to systematically setting parameters related to the structural model, the factor stuff, equal across groups. Traditionally starting with factor variances. Are those the same? If so, then we could test factor covariances. If so, then we could test factor means, and then that would be the end of it. And at this stage, it's not a problem if structural invariance doesn't hold. These are real differences at this stage. So let's see. Model 6, factor variance and variance. And no, there's not a better way to say that I know of. So I tested this by reconstraining the factor variance back to 1 in the alternative group. It was free before. I'm putting it back to 1. That answers the question, are there differences in factor variance? Did the model fit worse? Nope. And this is another instance in which I've only saved 1 degree of freedom, because I used to have 1 variance and I don't anymore. I put it to 1. And the model itself is still fitting pretty well, which is good. I don't have any factor covariances in this model, so the last step is factor means. And I have foreshadowing here because these are the Wald test results for the factor mean. It's fixed to 0 in the reference group and it's freely estimated in the alternative group. And this p-value right here tells us what we need to know. This is a standard hypothesis test in which the null hypothesis is 0. Well, lucky us, the thing we're comparing this to is also 0. Hey, isn't that convenient? So I know that if this number is different than 0 according to this test, then the numbers don't want to be the same, and I shouldn't constrain them to be the same. So this is called a Wald test. Estimate divided by standard error is treated like a z-test statistic. You should come to the same result if you did the proper likelihood ratio test, though, too, which I believe I did next. Yeah, I did. I went ahead and did it for the sake of demonstration, constraining the factor mean to be 0 in the alternative group here. And survey says, nope, not worse. So the p-value for the likelihood ratio test, comparing a model in which the factor mean is estimated in the alternative group to a model in which it is fixed to 0, had a p-value for that comparison of 0.27. And lo and behold, the p-value for the Wald test, 0.27. So should come to the same conclusion, if not the exact same conclusion. So putting it all together, it looks like the two groups do not differ in their factor means or their factor variances, and that's the end of the story. Structural invariance holds or doesn't hold? Holds. Structural invariance holds if you can constrain the factor parameters to be the same across groups and not hurt the model fit. See, all done. And here's some words. This is a lot of words. This is probably more words than you would want to use in a manuscript, but I'm writing it out for the sake of completeness. If you're doing a paper in which the whole point of the paper is psychometric evaluation, including invariance, you would probably provide more detail. If these are analyses that you did on your way to something else just to make sure you were headed in the right direction, then you might summarize this a bit more. But let me ask you this. Let's say that you are interested in differences in depression as a function of gender, and your advisor tells you to why don't you just do a t-test? Just add them up and do a t-test. Then you'll know if men or women have more depression. Now, what could possibly go wrong if you did that?
You wouldn't know which, like if the items are functioning differently.
Yes.
You wouldn't know within like each individual one whether they're functioning differently. You're like assuming that they all work equally well.
Mm-hmm.
And then you also wouldn't be able to see like across them if those items are working differently for men or differently for women.
Yes. Zoomers, did you hear that? A little bit? Or I'll repeat it for the recording just in case. Yes. The idea is if you just get a sum score and do a t-test to compare the means of the sum score. You don't know, let's say that women were higher in depression. You don't know if they're truly higher in the trait or if their expected responses are different because the items are functioning differently. Like let's go back to the items for a second here to be more concrete. I'll pretend I'm a clinical psychologist today. Why not? Who's going to stop me? They're all. Psych people, forgive me. It could be the case, for instance, that weight or appetite changes, right, are more important as an indicator of depression in women than in men, something like that. Certainly, we saw feelings of worthlessness and guilt have a different item response. So if you find differences, you don't know why you have the differences. And especially it could be the case if some of the items are invariant in one direction and others are invariant in the other. Those differences could wash out and you would think there's no trait differences, but really you have differential item functioning across items. Can I say that? Diff-diff? D-diff? Sure, I'm gonna make it up. D-diff, calling it right here. D-diff, if some of your items want to go up and some of them want to go down. Differential item functioning. You wouldn't know. But, so that it's not just invariance though. If you add items up into a sum score, what kind of factor model is that consistent with? It starts with a P. Vocabulary from like 2 months ago. P-A. We'll play hangman. P-A-R.
Parallel.
Yep, parallel. Parallel. Parameter, good guess. Most of the time that word would be right, but not this instance. No, parallel items. A sum score is the only way that you get the exact same trait that's correlated like 1 with the sum score is if your trait has a parallel items model underneath it, which means what are the constraints that make a parallel items model? There's 2. Yeah, the loading is the same across all the items. All items are equally discriminating, the idea of a Roche model, and one step further, not the intercepts, the other one. Nope. Item parameters is what I'm thinking of. Error, one more word?
Variance.
Error variance, there we go, yeah. Parallel items model has equal error variances across items and equal loadings. I have never seen that hold in practice for anything that has more than like 3 items, ever. It might in items that are constructed sort of algorithmically, like when you're measuring, subtraction in second graders or something like that, that's a reasonable thing, but not for these sorts of items, certainly not. Items that offer, that are individual, different types of aspects of the construct. So, adding up items and doing a t-test is logically inconsistent with the model that we fit. If you want to do your t-test, did we do one of those? Let me ask you that. Because you don't want to tell anyone, especially not your advisor, yeah, I can't do that. Lisa told me not to do that because that's dumb. That's not going to go over well. You don't want to tell them that you have a problem. You want to tell them what the solution is. So how am I going to be like, yeah, I can do your t-test? The answer is in front of you, actually, as usual.
Is it the means, isn't it?
Yep, factor mean difference. This is a latent variable ANOVA. That's where we're at the very end of all of this. You get to the last solution. I think it's close. Nope, this one. Yep, this is the last solution. We have tested measurement invariance. The extent to which the item relates to the trait is the same across all items. The extent to which the expected item response, conditional on a trait of 0, is the same across groups. We've evaluated for every item. It didn't hold for 7. And the extent to which the amount of not the factor variance is the same across groups. We did all of that stuff. So yeah, once you have all of that foundation underneath you, then you can believe this factor mean difference. Now, should I call it a t-test, though? Or should I use a different letter? We're back to introstat. Eh. It's further in the alphabet. Z, yeah, this is a Z. The difference, do you see degrees of freedom anywhere on here related to sample size? No, degrees of freedom in this context are all about the number of parameters, not the number of people. All of this stuff is Z's and chi-squares because we're not using denominator degrees of freedom. It's pretending we have an infinite sample. So you could actually take this test statistic, which is a Z, and turn it into a T if you use the T value with degrees of freedom equal to, I don't know, something close to sample size, I would say. There's not really like a rule, but sample size would be your starting off point. However, there's like 300 people in the sample, so it wouldn't make much of a difference. But yes, this mean difference test at the factor level is like your latent variable t-test or latent variable ANOVA. So that's your answer. This is what you can do instead. Okay, questions or comments on that? Okay, do you want to see a real world example that's not perfect? So that you're prepared when it happens to you?